Hello everyone. Today we will continue discussing our topics. So last session, let me just check. Yeah, it's shared. Okay. Last session, guys, we started in reviewing circuits and we discussed the ABC sequence and ACB sequence of Y connection systems, and we discussed also what the meaning of three windings connected in delta. Let's continue in our three-phase system discussion. So as we mentioned, guys, delta connection means three windings will be connected as follow. If the upper terminals are the starting ends, the starting terminals, and the last or lower three terminals are the end terminals. So every end will be connected to the next start like that, and the last end will be connected to the first start, and we can supply from here. Sorry. We can supply from the starts or ends, whatever. Okay, so this could be the start, the supply terminals here. Okay. So now, if this is going to be our supply, so this is terminal A, this is terminal B, this is terminal C. What we have now is our phase, which means our coil, is connected between two lines. This was not the case in Y connection. If we go back to the Y connection here, you will find that we have two phases here. Two phases means two coils connected between the two lines. These are lines A and B. So it's not the same connection or not the same volt. For that, V phase and V line were different in case of Y connection. So we have here V line equals √3 times V phase. And again, V phase means the volt across one phase, and phase means our impedance or coil. Okay? But this was not here the case in delta connection. Here we have the volt between A and B is the same as the volt across the phase. So we have here V line equals V phase in case of delta connection. So for ABC sequence, for instance, guys, if we assume that VAB equals V line at angle 0, so VBC would be V line at angle minus 120, and VCA is V line at angle 1 plus 20, plus 120. And for ACB sequence, if we consider A, B at angle 0, so CB would be at angle minus 120 and BA would be at angle plus 120. Okay, so this is the difference between ABC and ACB sequences. Okay, nice. Now we can convert, guys, from delta to Y. Okay, so converting from delta to Y, sometimes we need it in order to make calculations per phase. So we are not going to analyze circuits like you had in electrical circuit course, but we will just convert line to phase in order to make a single line diagram for our machines or transformer or whatever the machine we are working. So this is just the requirements. If you have delta connection, you would convert delta to Y in order to get the voltage magnitudes. And most of the time, we will not take care of the angles. Only in transformer, we may calculate the angle to calculate by the MV what's called the group number of the transformer, and we will discuss this later on. So this is now the delta connection. Now, guys, if we assume that we have Y connected supply connected to Y connected load in 4-wire systems, so you can see here that for the 4-wire system, the phase A of the supply is connected to phase A of the load. phase B and C are the same, and neutral point is connected as well. If you guys would see the current values, you can simply say now, since this point and that point are the same, this point and that point are also the same. So this means VA is connected in parallel with the load ZA. So you can simply say IA equals VA divide ZA. Correct? So we can say now I phase equals V phase divide our impedance. This is simply what we need. And by the end, the phase shifts will be according to the angle minus or plus 120. This is the case, guys, we have, correct? So this is for the Y-Y connection. What about the power? For balanced three-phase systems, guys, and this is going to be the case all of the time in our electrical machines courses. So for a balanced three-phase system, we have the definition of active power equals 3 V phase I phase cosine theta, where theta is theta V phase minus theta I phase. Take care of that definition. All of the time, the power factor angle is the angle between V phase and I phase, not V line and I line. Okay, guys? So all of the time, power factor angle is cosine V phase minus theta V phase minus theta I phase. So we can say, in another term, is 3 V phase I phase power factor. So this would be the active power, P average or P active of the three phases. Now, in case of line, if you are going to calculate the power from the line values, whatever Y connection or delta connection, so if it is Y connection, for instance, we can say that V phase equals V line divided root 3. So 3 times V line divided root 3 times I line times cosine theta. Why I line here? Because we can say in Y connection, I phase and I line are equal. So this is in case of Y connection. And it's going to be the same as phase connection. We will see that right now, just a moment. So now the power is going to be root 3 times V line, I line, and the same cosine theta, which is theta V phase minus theta I phase. So whatever the term here, cosine theta all of the time is cosine theta V phase minus theta I phase. So this is another term of power. So we can say by the end, power can be root 3 V line I line cosine theta or V phase I phase cosine theta, and all of the time theta is the power factor angle, which is theta V phase minus theta I phase. If you'd like to calculate the reactive power, so the reactive power, just replace cosine by sine. So these are the relations of active and reactive power in three phase. For the apparent power, guys, you know that power equals P plus or minus JQ. So by the end, it would be root 3 V line I line. Okay. In case of 4-wire system, neutral current equals IA plus IB plus IC. And this would be 0 all of the time if the load is balanced. Because if you have IA equals IB equals IC in magnitude, and the phase shift is 120 degrees, so the summation is going to be 0 all of the time. Okay. Nice. For the delta connection system, so the analysis will be the same. We can say here IAB, which is I phase, equals VAB divided ZAB. So this is going to be I phase. And after calculating I phase, you can get the I line. How can I get I line? Simply apply Kirchhoff current law here. So we can say IA plus ICA equals IAB. So this is, for instance, the phasor diagram. Here we have IA. This is IA. And sorry, we have IAB, the phase, we calculated the phase firstly. So this is IAB that we already calculated. And we have also IBC. So this is IBC here. If you would like to get IA from IAB and IBC, so this is IAB, this is IBC. So let's, sorry, not IBC, IAB and ICA. So this is ICA. So apply at this node. So we can say IAB minus ICA. Okay, so let me write down this here. So I can say here at this node, IA, this is entering the node, plus ICA entering also the node, equals IAB, which is exit the node. So I would like to get IA, so I can say it's IAB minus ICA. So this is IAB, this is ICA, so minus ICA is here. So the resultant vector is going to be this vector. So this is IA. So we can say if you have phase current and you would get the line current, you can say I line equals √3 times I phase, and the angle would be shifted by minus 30 degrees. So this is the relation in case of delta connection. So we can say by the end, I line equals √3 I phase. So this is in delta connection. And this is the part we just made on the phasor diagram. So by the end, I line equals one of the letters, IA or IB or IC, equals √3 times I phase. So this is what we need. We don't need a lot of analysis here in electrical machines, like in the electrical circuit course, but just the relations between line and phase voltages and currents. Okay. So we can say now, guys, for the delta connection, still the power equals 3 times the single phase power. So it's 3 times one phase volt, which is VAB, times IAB, for instance, cosine theta. And again, cosine theta, still theta equals theta V phase minus theta I phase. All of the time, guys, theta is the power factor angle, which depends on phase volt angle minus phase current angle. So 3 V line, because V line equals V phase, which is VAB, times I phase, which is IAB here, for instance, times cosine theta. If you would like to get the I line as a function of I phase, we can say, since we have I line equals √3 times I phase, so we can say I line divided √3 equals I phase. So let's replace I phase here by I line divided √3. So we can say the power equals √3 times V line times I line cosine theta. The same relation we have in Y connection. And the same is also for reactive power. We just replace cosine by sine. So we end up with the same relation, guys. So now, whatever the connection, guys, we can have now a general form for power. What are these forms? I can write this form right here. Whatever the connection, we have P equals √3 V line I line times power factor, or cosine theta, where power factor equals cosine theta V phase minus theta I phase. I insist to say it every time. Take care. It's not V line and I line. All of the time, power factor angle is cosine theta V phase minus theta I phase. Or you can say power also equals, or power equals 3 times V phase times I phase times power factor, whatever the connection. And by the end, S equals √3 V line I line equals this is its absolute value, okay, equals 3 V phase I phase. Q, guys, just replace the cosine by sine. So I can write down Q here equals root 3 V line I line sine theta V phase minus theta I phase, or 3 V phase I phase sine theta V phase minus theta I phase. So these are the relations of active power, apparent power, and reactive power, whatever the connection, Y connection or delta connection. All of you guys know the conversion from Y to delta or delta to Y if we have balanced load. So we can say the ZY equals Z delta divided 3. Okay, so this is the relation between the balanced delta and Y. What's the meaning of per phase equivalent circuit? Now, guys, since we will have balanced three-phase systems in our circuits, so we don't need to draw every time the three phases. We can just replace the circuit by a single phase because it's going to be just repetition for the drawings and calculations. So we can just consider what's called per phase, or sometimes we call it single line diagram. So if you see in the electrical drawings, you will see what's called single line diagram. So single line diagram means this is a single circuit of a three-phase system. Okay, I can show you some examples. Let me just grab it with you now from Google. Just here to see single line diagram of any power system. Let's say for any power system. So I can, let's see, yeah, let's see this one together. Okay, so can I copy this one here? Okay, I can copy that one, so it would be easier to discuss it right here. Okay, this is great. So let's see this together, guys. So what we can see here is, here we have something called EHV bus. Maybe this is extra high volt. I don't know what this EHV stands for. Okay, so any plan like that, guys, would have a key with every symbol. What the meaning of every symbol? Okay, so I'm assuming that EHV may be extra high volt bus. So this is a bus bar, okay, with a certain voltage magnitude. I don't know this voltage magnitude, but I can say this is here a bus. Okay, this bus is connected here to something here called E. This is most probably a disconnecting switch, okay, or circuit breaker, and then it's connected to this symbol. It's transformer. This is a symbol of transformer. Okay, they call it here GT, maybe the generating transformer. Okay, so this is here generating transformer because it's directly connected to the generator bus. Okay, sometimes, guys, you may find this symbol here, this 3 dashes, which means this is repeated 3 times because this is three-phase system. So this is called single line diagram, but we have 3 of this one. Or sometimes you can find it like that. It's just 1 dash and written here 3. Okay, so this means it's a single line diagram and this represents a three-phase system. So this is a symbol of transformer. Here, this is a symbol of a generator. This is another transformer here connected to another circuit breaker, to another bus bar, and so on. So this is how to read a single line diagram. Okay. And here, as you can see, this is EHV, maybe extra high volt. This is a generator here connected to a certain voltage level. And here we have another transformer connected to 11 kilovolt bus bar. So this is 11 kilovolt. Okay. So this is, guys, called the single line diagram. And on a single line diagram, everything is drawn in single phase and it represents three phase systems. By the way, guys, in our power systems, we have only three phase systems. But for electrical machines, you may have multi-phase machines, like for instance, 5-phase or 6-phase machines. We can have multi-phase machines like 5-phase or 6-phase or whatever. This is for reliability, okay? Because multi-phase machines are much more reliable than 3-phase machines. However, we do prefer 3-phase systems in power system because of the cost. So cost-wise, the 3-phase is much better compared to other phases, other type of multi-phase systems, because it's going to be very expensive. Okay, so this is called, guys, single line diagram. We refer to that by what's called SLD, single line diagram. So I just grabbed any example for a single line diagram to show you how to read a certain drawing. Okay, let's go back to our slides again. So for our power system, we do prefer to have what's called per phase or single line diagram. So per phase equivalent circuit is going to make just one phase circuit instead of repeating the 3-phase circuit. Okay. So when we can use this per phase, guys, we can use it if the 3-phase system is balanced system. Because if you have unbalanced, this means every phase will have different impedance. So we cannot have a single line diagram. We cannot have per phase equivalent circuit in this case. So in our classes, we will convert every 3-phase machine, guys, into just a single phase or per phase equivalent circuit. Because we will assume that all of our electrical machines are balanced 3-phase machines. It depends on using one phase of Y connection load and source. So for instance, if you have Y connected load and source, okay, so in this case, you can convert your system easily to a single phase. But if load or source both are delta connection, it has to be transformed to Y connection. So if you have one of the source or load as delta connection, guys, you need to convert that to Y in order to make a single line diagram or to make a per phase equivalent circuit, because you cannot connect delta connected systems in series, correct? But when you connect Y connected systems in series, it's possible. What I mean is, let's go back a few slides to show you here, guys. Not here. Yeah, just here. Okay. So here, guys, this supply is Y, and this load is Y. I definitely can say VA is connected in series with ZA, correct? But even if we have transmission line, I assume that this is the generation, this is the load, and I have transmission line in between. So I can connect all of them in series together. But if the system is delta, if you have supply is delta, or transmission line is delta, or any other system in delta, we cannot connect in series anymore, correct? So because of that, guys, if you have any delta connection in your circuit, you need to convert that to Y in order to make a single line diagram or per phase circuit, okay? Therefore, delta load, for delta load, we should convert to Y. So we can say ZY equals Z delta divided 3, and VA, which is the phase volt across the phase equals VAB divided root 3 equals the line to line voltage divided root 3. Okay? Someone can say in delta connection, we have V phase equals V line. This is correct. But now we don't have delta anymore. I'm converting delta to Y, which means we are converting delta to Y, so I need to get the equivalent Y. And the equivalent Y would have phase volt different to line volt. So let me go back. Where? No. Not here. I could see that in one of the slides. Just a moment. Yes, here. So can you see, guys? This is here delta. So in the red line here, this is the delta. If you convert delta to Y, so I'm going to draw with different color. So this is the Y. So Y is the equivalent Y of our delta. Can we say for the equivalent Y now, V phase equals V line? No. Because the equivalent Y is a Y connection. It's not delta connection anymore. So if you would like to get the V phase of the equivalent Y, you have to say V phase equals V line divided root 3. You got my point, guys? So even if the system is delta connection and you would like to get the per phase equivalent circuit, you have to get the V phase as V line divided root 3. Okay, so this is the rule why we may need to convert from delta to Y in our course. Okay, now I'm gonna solve with you one example, and from this example we'll discuss one thing regarding power measurements, which is gonna be the last topic we will discuss it in our class today. So we will end up with this example and the theory, how can we measure power using 2 wattmeter method. Okay, so it's going to be relatively long example, so let's start solving this together. So in this example, guys, in the 3-phase balanced system shown in figure, so this is our figure here. So we have the load is Z equals 8 plus J 6, and consider VAB is 200 angle 0. So as you can see, guys, we have delta connected load. So Z, as you can see, Z of every phase are equal. So we have balanced 3-phase system. The impedance per phase is 8 plus J6. And VAB is the line volt. So this is A here, this is B here. So the line volt is 200 volt at angle 0. So it provides me with the angle. So angle, guys, is something virtual. It's not something we will measure using voltmeter, for instance. Okay, so for voltmeter, it can measure just the RMS value. But here he gave you in this example the reference of AB to have it as a reference in your solution for all of this power system. Okay, and he mentioned here it's RMS volt. It's not important to mention that because all of the time we refer to the volt by RMS value. And he mentioned that the sequence is ABC. Also, we don't need to mention that because the default is ABC sequence. Now, what do we need to do in this example? Determine the phase currents. So firstly, we need to get the phase current. Phase current means the current through the impedances. So this is the first thing. Second, determine the line currents. So we will get the line currents as a function of the phase currents, as we already knew how to calculate that. Then determine the total 3-phase power. We will calculate the 3-phase power. Draw the phasor diagram of currents and voltages. So draw the phasor diagram for all currents and voltages we calculated in the power system. Then last thing is calculate W1 and W2. W1 and W2, what are these two devices? We will elaborate more. What are these devices? What is the device that can be connected in this shape? So we will elaborate more here and see how can we calculate the reading of W1 and W2 and comparing these readings with the value of W1 plus W2 to the total absorbed power calculated in part. Where is the power calculation? Yeah, in part C. Okay, so we'll calculate these two parts C. So let's take it step by step. So let's start firstly with determine the currents of this power system. So starting with the current, guys. So firstly, we have the impedance. So I can say that for delta connected load, the I phase equals V phase divided V phase. So V phase equals 200 volt at angle 0. The impedance here is 8 plus J6. If you convert the rectangular form to the polar form, it would be 10 at angle 36.9. So the IAB equals 20 ampere at angle minus 36.9 degree. So this is the phase current we have here. Do I need to calculate the other three phases? Sorry, the other two phases? We don't need. We just can shift the angle. So I can say, since this is IAB, so IBC would be 20 at angle minus 36.9 minus 120, which is going to be minus 156.9 degree. The same is for ICA, so I can say ICA is 20 at angle minus 36.9, which is the angle of phase A, or the first phase, plus 120, which is 83.1 amperes. So this is, guys, how can we calculate the three phases currents. So this is the first part, the three phases current. For the line currents, you can use Kirchhoff current law or calculate the line current by the relation we just mentioned. So IA equals IAB minus ICA. So it's 20 at angle minus 36.9 minus 20 at angle 83.1. So the result would be the 20 times root 3, which is 34.6. And the angle is the angle of the first phase AB minus 30 degrees, which is minus 66.9. And you can do the same for the third, for the other lines. So the same magnitude and shift the lines by minus 120 and plus 120. So this would be the three line currents. Now, power. We need to calculate the power. So we mentioned before, guys, power of a three-phase system equals root 3 V line I line power factor, where power factor is cosine theta V phase minus theta I phase. You can also calculate power factor as cosine theta of your impedance. Okay. So we can say here 3 V phase I phase. So this is 3 V phase I phase. Cosine the theta of our impedance. So this is the power, guys, here. Or root 3 V line I line cosine theta. So by the same way, it would give you the same amount. So still here, this is just a circuit problem. You already learned that in electrical circuit. Now let's move to the next important part of our discussion today, which is how can we measure the three-phase power? This is the phasor diagram, guys. I'm gonna leave this one for you. You already know now how to draw the phasor diagram. Let's focus now on the power. How can I measure the three-phase power? This is a simple diagram for the wattmeter connection in a way called two wattmeter method. So if you would like to measure a power of a single phase, let me draw that, guys, in a new slide here. So I'm going to add one more slide here. So if I have a single phase load, I'm going to draw that here. I have here a load, whatever the load type, I don't know the load. And here is the supply. It's connected to the neutral point. So this is the neutral point, and this is the line, and this is a single phase. Okay. So this is a load here. I'd like to measure the power. You know that if I'd like to measure the current, I can add an ammeter in series. If I'd like to measure a volt, I need to add a voltmeter in parallel. What about the wattmeter? Or how can I measure a power? Power can be measured by a device called wattmeter. So the wattmeter, guys, internally has two coils. One coil connected in series to measure the current, and another coil is connected in parallel to measure the volt. So this is the device which is called wattmeter. So by the end, wattmeter will have three terminals, as you can see. Two terminals to be connected in series with the circuit to measure the current, and the third terminal to be connected in parallel with the load to measure the volt. And internally, it will calculate the power. Okay, so I'm not going to discuss internally what is happening in the wattmeter. So the wattmeter is already something called moving iron device. So it has two coils inside, and it has a pointer. This pointer is going to move according to the average power absorbed through the coil, and the coil is going to move as a function of V times I times cosine theta V minus theta I. So this is the concept of the device and how the wattmeter is working, but this is not our topic today. So we need just to know how to connect the wattmeter to measure the power in our circuit. So we have three terminals. Let me connect that in different color here, in green color, for instance. So I will connect the wattmeter as follow. I have the current coil of the wattmeter, I have the voltage coil of the wattmeter, and this is our device boundaries. And the third terminal here is going to be connected in parallel like that. So this is now wattmeter connected to a single phase. So it's making sense to us. If we have three-phase system, we can have 3 wattmeters to measure the power of every phase. So I'm going to draw now a Y-connected load. If I have Y-connected load like that, let me say it's RL load. With our terminals A, B, and C like that. And we need to connect wattmeter to measure the power of this device. And we have here a certain supply with our terminals A, B, and C. Let's have this B. This is easier in connection. Okay. How can I measure the power now using the 3 wattmeters? So I'm going to draw the wattmeters in different colors. Start firstly with this color. So I can say for the first phase, this is going to be the current coil, and the voltage coil can be connected in parallel with the load. So this is a neutral of my load. So I can simply connect this to the neutral point here. And this would be our first wattmeter. And this is going to be wattmeter for phase A. Now, I'd like to connect the wattmeter of phase B. Let me connect that in a different color. So the wattmeter of phase B, I will connect the current coil, and the voltage coil is here, will be connected also in parallel with the phase B volt like that. So this is going to be wattmeter B, and this is the current coil will be connected to phase B. And the last one is C. Let me connect that also in a different color. So this is going to be the current coil, and the voltage coil is here, will be connected also to the neutral point. And then this can be connected here to phase C, and this would be the third wattmeter, wattmeter C. And definitely I can say power total equals the reading of wattmeter A plus the reading of wattmeter B plus the reading of wattmeter C. So this is makes sense because we have three-phase system, so we have three-phase or 3 wattmeters. However, we could find that if we play with the relations of the wattmeter and a certain way to connect these wattmeters together, we can just use 2 wattmeters to measure the power of a three-phase system. What if this way? This is what's called 2 wattmeter method. So let's see, guys, what is this method and how can we make this calculation. So simply, I'm going to say firstly, this is A, B, C system. This is positive system, positive sequence system. I will have 2 wattmeters. The first wattmeter is going to be connected between or to measure phase A and the volt of A and C. So W1 is going to be the negative sequence, and W2 is going to be the positive sequence wattmeter. Why? Again, can you see here, guys? So wattmeter 2 here is connected to measure phase B current. So this is the current coil, and the voltage coil is connected between B and C. You know that if I have A, B, C, so B and C is positive, A and B is positive, C and A is positive. So if I measure AB or BC or CA, this is positive sequence. So the first or the second wattmeter here, W2, is measuring BC volt. So this is positive sequence wattmeter. The other wattmeter, W1, is measuring the first current, which is IA, and the voltage coil is connected between terminal A and the same common point, C. It cannot be connected to B. So the idea is when you connect the 2 wattmeters, the 2 wattmeters voltage coils have to be connected to a common point. So if you connect the current of the 2 wattmeters to A and B, so the common volt point should be C. You got it, guys? So this is the way of the connection of the 2 wattmeter method. And again, since wattmeter 1 is measuring, or voltage coil of wattmeter 1 is measuring the AC, and AC is not positive sequence, so this is going to be negative. And we will reflect the negative in our relation right now. Okay? And the same is also here. So here we have the voltage coil of the wattmeter 2 is connecting to VBC. So VBC is positive sequence. So we will have positive sign in our relation for wattmeter 2. What is the relations? What are the relations? So relation 1. Wattmeter 1, which is W1, is the negative sequence. So it's going to be V line, I line, cosine theta minus 30 degrees. What is theta? Theta is the power factor angle. So I can write this down here. W1 equals V line, I line, cosine theta minus 30. And I say this is minus. Why minus? Because W1 is the negative sequence voltage coil. So this means when I write W2, I should say W2 equals V line, I line, cosine theta plus 30 degrees. We found that if you add W1 plus W2, it would give you the same amount of total power. So P total equals W1 plus W2. And this is called the 2-watt meter method. There is a derivation for this relation, guys. How can we get the relation from the 2-watt meter relations here and calculate the power? And this is just a simple relation here. So if you have this one here, V1 I1 cosine theta minus 30 plus V1 I1 cosine theta plus 30, you know that there is a relation for cosine A plus P or cosine A minus P. If you use these relations here, you will end up with the total result is going to be root 3 times V1 I1 cosine theta. And you know that root 3 V, sorry, not V1, V line, root 3 V line I line cosine theta. And you know that root 3 V line I line cosine theta is nothing but the total power of your system. By the way, there are some other relations, guys, for the reactive power and power factor using the 2-watt meter method. I'm going to share some materials with you. Please have a look to these materials to know more about the 2-watt meter method. But the most important thing to me here to understand how to connect the 2-watt meter method to measure the power of a 3-phase system. We will have one experiment on that in our lab when we start our lab dwelling. Now, let's do that in our question. So in our question, guys, let me go back here. So in our question, we already have the V line and I line. So can you see here? This is the value of I line, 34.6. And V line equals V phase here equals 200 volts. So we have V line equals 200 volts. We have I line equals 34.641 ampere. And you know that theta is the power factor angle of the impedance we have right here, which is 36.9. So theta equals 36.9. So these are the three values just we need to calculate the readings. Now, I'd like to go back again to the watt meters connected to the power system here. The question, which watt meter is positive and which watt meter is negative sequence? So if you have a look here, guys, you will find that watt meter 1 is connected between A and B. Watt meter 2 is connected between C and B. So if you write here A, B, C, so you will find AB is positive. So this means watt meter 1 here, the voltage coil of watt meter 1 is connected to AB, so watt meter 1 is positive. So I can say the reading of watt meter 1 equals V line, I line, cosine theta plus 30. And by default, W2 would be the negative. So V line, I line, cosine theta minus 30. So this is the way, guys. Okay, so we can now substitute in the relations and calculate W1 and W2. So here is the calculation. W1 is the positive sequence. So here, as you can see, here he wrote according to the connections. I don't care about that because by the end, this is balanced 3-phase system. So VAB is nothing but V line, IA is nothing but I line, and cosine theta plus 30. And the other one is cosine theta minus 30. And the total here, get W1 and W2, add the two values together, and you find that it's equal to the same amount of 3-phase power. Okay, guys. So this is what we need from the 2 wattmeter method. By the way, here in this example, the value of cosine theta plus 30 and cosine theta minus 30 provide positive values. You know that if I draw the cosine waveform, this is the cosine waveform, guys. So this is 0 degree, this is 90 degrees, and so on. So this is 180 and so on. So this means if the angle is negative in this side, so the cosine is going to be negative. So here we were lucky because theta is more than 30 degrees. But what will happen if you have theta equals, for instance, 25 degrees? So 25 plus 30 is fine. But 25 minus 30, this value is going to be negative. Do we have something called the power in negative? Actually, we don't have. But this is right if we connect this wattmeter to a single phase. This wattmeter device now is not connected to a single phase anymore. It's connected between two phases. So if you have the value of the wattmeter in negative sign, please don't neglect the negative sign. Consider the negative sign, which means if I have the first value is 1000, then second value is minus 100. So this means total power equals 1000 minus 100 equals 900 watts. So please consider the angle with the negative sign, and if you have the reading of the wattmeter in negative sign, please consider this negative sign as well. Okay, because again, this doesn't mean that the power is reversed, but this means the wattmeter is not connected to a single phase, which means it's not the power absorbed for one phase. It's a different relation now. How can you see that in the lab? You would see the pointer of the wattmeter going to the opposite side. So in this case, if you would like to get the exact value, reverse the connection of the pointer in order to get the other reading. So this is the way we can do. Okay, guys. So this is, guys, a summary for the power measurement of the three-phase system. I think we covered now most of the materials we need as introduction to our course. So we covered the concept of power factor compensation and power factor correction. We covered the different connection of three-phase systems in case of load or supplies, the power calculations for three-phase systems, the transformation between delta and Y connection and why we need it and when we were going to use it in our classes, the different method to measure the three-phase power. We discussed the three-phase wattmeter and the 2 wattmeter method. So this is most of things we need from three-phase systems and AC that will help us in our course topics during this semester. Thank you so much and see you in the next class.